June 30th, 1908, Siberia. An explosion flattened 80 million trees across 800 square miles. The blast's energy exceeded Hiroshima's by 1,000 times, yet no impact crater nor meteorite fragments were found. The Tunguska event occurred at 7:14 a.m. near the Podkamenaya Tunguska River in central Siberia, Russia. The powerful explosion happened at an altitude of 5 to 10 kilometers above the ground. This colossal explosion devastated an area of over 2,000 square kilometers. The blast flattened some 2,000 square kilometers of forest, charring more than 100 square kilometers of pine forest. The sheer scale of devastation covered an area of about 2,150 square kilometers. This vast, flattened expanse of Siberian taiga was equivalent in size to a small country or a major U.S. city. Reindeer herders and other locals in Evenki reported seeing a brilliant blue-white fireball streaking across the sky. This fiery spectacle preceded the enormous explosion and shockwave that followed. The resulting shockwave was incredibly powerful, reportedly knocking people off their feet hundreds of miles away. Windows shattered in distant settlements, and seismic instruments registered tremors across Eurasia. In the nights following the blast, the skies over Asia and Europe shone with an unusual glow. This phenomenon suggested vast quantities of fine dust particles were suspended high in the atmosphere. Despite the enormous destruction, the Tunguska event initially garnered little attention, even within Russia. The remote location and political climate meant detailed scientific investigation was delayed for years. The first official expedition to investigate the blast site didn't occur until 1987. Soviet scientist Leonid Kulik led this crucial journey, hoping to find evidence of a meteorite impact. Kulik's team confirmed the trees were arranged in a unique pattern, knocked down radially outwards from a central point. However, their most puzzling discovery was the distinct absence of a central impact crater. For decades, scientists have grappled with the central mystery. How could an explosion of such immense power, capable of flattening millions of trees, leave no distinct impact crater behind? Compounding the mystery, extensive searches yielded no large meteorite fragments. This absence of physical evidence made pinpointing the exact nature of the celestial object even more difficult for researchers. The most widely accepted theory suggests a stony asteroid entered Earth's atmosphere. It exploded at an altitude of 5 to 10 kilometers, creating powerful shockwaves, but no direct ground impact. The energy released by this atmospheric explosion is estimated to be between 3 to 50 megatons TNT equivalent. This represents hundreds of times the power of the atomic bomb dropped on Hiroshima. Another significant hypothesis proposes the Tunguska object was a comet, largely composed of ice. Upon atmospheric entry, it would have vaporized completely, leaving no solid fragments or impact crater. After later expeditions, scientists found microscopic spherules containing nickel, iron, and silicates in soil samples. These particles, found in areas of devastation, are consistent with meteorite dust or vaporized comet ice. Analysis of tree rings in surviving and fallen trees revealed anomalies following 1908. Sudden changes in growth patterns and evidence of burning suggest the intense heat and shock waves' impact. Modern atmospheric modeling attempts to simulate the event. These complex simulations help scientists understand how an object of a certain size and composition would explode at that specific altitude. Estimates for the object's size vary significantly, from 50 to 200 meters in diameter. Such a range reflects the difficulty in precisely determining the size and composition from indirect evidence alone. This object likely traveled at immense speeds, estimated around 27 kilometers per second, or over 98,000 kilometers per hour. It approached from the east-southeast at a relatively shallow angle. The baffling nature of Tunguska has fueled more speculative theories. Ideas have ranged from mini black holes and antimatter explosions to alien spacecraft or even failed technological experiments. The Tunguska event highlighted humanity's vulnerability to cosmic impacts. It spurred increased scientific interest and later efforts in planetary defense, aiming to track and mitigate potential asteroid threats. Over 1,000 scholarly papers have been published on the Tunguska explosion, mostly in Russian. This volume underscores the event's enduring scientific fascination and its role in shaping impact research. Despite extensive study, the Tunguska event remains a captivating enigma. Its legacy lies not just in the destruction, but in the persistent questions it poses about our place in the universe. The explosion's force felled an estimated 80 million trees, a stark testament to its power. This widespread destruction occurred across an immense area of approximately 800 square miles in this remote region. The devastation blanketed approximately 800 square miles of the Siberian wilderness. This colossal area underscores the sheer scale of the event, dwarfing many terrestrial disasters in its geographical footprint. The Tunguska explosion's estimated energy yield was more than 1,000 times greater than the atomic bomb detonated over Hiroshima. This immense power explains the unprecedented scale of destruction across Siberia. A key feature of the Tunguska event is the complete absence of any significant impact crater at the presumed ground zero. This anomaly baffled investigators from the outset. Search expeditions, including those led by Leonid Kulik, failed to recover substantial meteorite fragments. This scarcity of physical evidence added significantly to the mystery surrounding the event's cause. Local Evenki reindeer herders described seeing a huge, blindingly bright fireball. This visual phenomenon, moving across the sky, was the first sign of the impending catastrophe. The explosion produced a tremendous roar, audible hundreds of kilometers away. This thunderous sound was reported by people in settlements far from the epicenter, attesting to its immense power. Instruments in Europe, thousands of kilometers away, registered the atmospheric pressure changes and seismic tremors. This distant data provided crucial early evidence of the event's magnitude and reach. Despite immense logistical challenges, Leonid Kulik led multiple expeditions to the site. His determination in the 1920s and 1930s was instrumental in bringing scientific attention to the phenomenon. Kulik meticulously documented how trees were felled radially outwards in all directions from a central point. This specific pattern was a key clue to understanding the explosion's origin. The absence of a crater remained the biggest puzzle for Kulik and subsequent researchers. If it were a meteorite, a significant impact crater should have been present, but none was found. As evidence trickled in, major scientific theories began to form. The leading explanations focused on celestial bodies exploding high in the Earth's atmosphere, not impacting the surface directly. The stony asteroid airburst theory posits a solid rocky object entered the atmosphere and detonated due to intense pressure and heat. This validated the observed devastation without a crater. The cometary origin hypothesis suggests an icy celestial body disintegrated upon entry. Comets, made of ice and dust, would vaporize completely, explaining the lack of fragments and crater. Subsequent soil analysis revealed microscopic spherules rich in elements like nickel and iron. These particles, found selectively in heavily affected areas, provided tangible, albeit minuscule, extraterrestrial evidence. These microspherules contained specific mineral compositions, including nickel iron and silicates. Such chemical signatures are often associated with stony meteorites or extraterrestrial dust, lending credence to impact theories. The study of tree rings or dendrochronology revealed unusual growth patterns post-1908. Scientists detected abrupt changes suggesting the intense heat and shockwave disrupted normal biological processes. In some fallen trees, evidence of burning was found, particularly on the side facing the explosion's direction. This suggests intense thermal radiation accompanied the powerful concussive force. Modern scientists use sophisticated computer models to simulate atmospheric explosions. These simulations help test how different objects would behave upon encountering Earth's atmosphere at high speeds. Estimates for the inbound object's size range widely, from 50 meters to as large as 200 meters in diameter. This uncertainty highlights the challenge of piecing together events from indirect evidence. The object was estimated to be traveling at approximately 27 kilometers per second. This incredible speed meant it would have entered Earth's atmosphere with tremendous kinetic energy, leading to a rapid explosion. Its approach angle from the east-southeast was observed to be relatively shallow. This trajectory facilitated its interaction with the atmosphere over a longer duration before its ultimate catastrophic detonation. The unique circumstances have led to speculative theories beyond asteroids or comets. These include cosmic strings, antimatter impacts, or even highly advanced experimental terrestrial technology. One such exotic idea is a mini black hole passing through Earth. While scientifically improbable given the lack of evidence, it highlights the extreme nature of speculations. Another fringe theory suggests an antimatter object impacted Earth. Annihilation with ordinary matter would release immense energy, fitting the Tunguska blast scale, but the required antimatter quantity is vast. Certain speculative theories wonder if the event was caused by a catastrophic failure of advanced yet unknown technology from either terrestrial or extraterrestrial origins. Evidence remains purely conjectural. The Tunguska event served as a stark reminder of Earth's vulnerability. It catalyzed efforts to detect, track, and catalog near-Earth objects, forming the basis of modern planetary defense. Studying Tunguska helps scientists understand the physics of airbursts. This knowledge is vital for predicting damage from future impacts, whether from asteroids, comets, or other celestial bodies. Since 1908, over 1,000 scientific papers, many in Russian, have delved into the Tunguska phenomenon. This vast body of research testifies to its enduring scientific significance and mystery. The Tunguska event remains one of the 20th century's greatest scientific mysteries. Its combination of immense power, remote location, and lack of clear evidence fuels continuous fascination and debate. The Tunguska explosion serves as a powerful reminder of the dynamic universe we inhabit. It highlights that Earth is not immune to the unpredictable forces shaping the cosmos. Despite numerous studies, scientific debate persists regarding the precise nature of the Tunguska object and the exact mechanism of its explosion. Ongoing research continues to refine our understanding. The consensus leans towards an atmospheric airburst of a meteoroid or comet fragment. This scenario best explains the widespread flattening and the absence of a large, definitive impact crater. The sheer force of the shockwave, a direct result of the rapid atmospheric expansion, was responsible for much of the destruction. This pressure wave traveled faster than the speed of sound. The Tunguska event's lessons are crucial today. Understanding potential cosmic threats enhances our preparedness and informs global strategies for safeguarding our planet against future impact events. For over a century, the Tunguska event has inspired awe and scientific inquiry. It remains a compelling case study in astrophysics, geology, and the enduring mystery of our solar system. The Tunguska event, though mysterious, is a vital piece in understanding our planet's cosmic history. Join us as we continue to explore the universe's secrets and protect our future.